Yeah, first of all, thank you very much for the invitation. I excuse myself that I speak English. You can already see that my French is very bad from the mistake that I just noticed down here. When I looked at the posters, that I realized that I did the wrong word. So I want to speak about extended Lagrange subspaces. And Lagrange is everywhere in my mathematical life, and part of it you will see here. So let me start. We have seen a lot of historical remarks about, and I might add when I researched for this talk, I realized that he became a teacher for mathematics at the university already with 19, which is usually when people nowadays start to study. He was also a founder of an academy at a very young age. And when he came to Berlin, when Friedrich II of Prussia offered him the directorship, that's also an amazing thing. I don't know whether you know that Frederick II suffered very much from his father, who was a pure soldier but never made any war, while Friedrich II was treated very badly as a child, and he always had to sit with his father and the generals and every evening and talk soldiers, talk war. And when he became the king, he wanted to change this, and he wanted to change it to science and arts and literature. And so he invited a lot of famous people to his court, including Voltaire, and he only spoke French. So he hardly spoke any German. But in contrast to his father, he started the war right away. So that's a thing that he learned from his father. So when Leonhard Euler went back to St. Petersburg, Lagrange came to Berlin, and he stayed there until a year after the death of the king, when he moved to Paris. And also that wasn't mentioned that he would have been banned from France in the revolution because he was a foreigner. He didn't have the French passport, but he got an exception. And later on he was made senator. So he lived in this house in Berlin. He was the second owner of the house. This is called the Magnus House. Nowadays, when you go there, there's always a policeman standing in front of this house. This house is now owned by the German Physical Society, and they have also meetings in part of the house. If you know Berlin, this is the Pergamon Museum, and the house is just opposite of the entrance of the Pergamon Museum. And the reason why there is a policeman is because there is a physicist called Angela Merkel and her husband who live in that house. We have their a private apartment in the house. So this is, and it's you can have meetings there, physics meetings, and you might run into the chancellor. Okay, so much for history, and now if I talk about my own work, then Lagrange is everywhere, because if you look at mathematical modeling of today and numerical mathematics, that's very much Lagrangian, much more than Eulerian in the development. And so I always say that modern key technologies, and I will give you an example, need modeling, simulation, control, and optimization of complex dynamical systems. And most systems are multi-physical, so they consist of different mechanics, electronics, and other devices. Just look at your car, and you realize very quickly that it's not just a mechanical device anymore. It's very different physical phenomena that are, and the phenomena work on different accuracy and on different scales. And the other thing why Lagrange comes into the game is that modeling nowadays is highly automatized. This started in the 50s and 60s in the electronic circuit world, but it's now everywhere. So if you go to into a research and development department of any big car manufacturer or at Airbus or any other places, any device is put together from little pieces, from modules. And this is nice from the point of view of modeling, and we will hear about that, but it's also gives a lot of headaches for the numerics and the control. And the philosophy that should happen is that modeling, analysis, numerics, control, and optimization should go hand in hand, which they don't yet. And I think the right way to do this is a Lagrangian paradigm that needs to be adopted. So let me go a little bit more deeper into this. So if you look at this computer, there's all kinds of devices on that computer. I mean, chips, there's mechanical devices, or mechanical and optical devices, and all these pieces are put together on different levels. And they're put together as a network. And on the border between two different devices, say a circuit and the bus system or something like that, there is an interface. There is a constraint. And we've heard yesterday in the talk of Gerd Wanner very nicely that bringing in the constraints in a good way, that's Lagrange, using Lagrange multipliers. And I will have a few more examples. So if you now look at what's happening in industry, they're using packages like MATLAB Simulink. I'll use the mechanical device. Or Simscape. There's a new language called Modelica, which is really like Lego. You get equations, you take them from the screen, you click, 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 you put some connectors in between, and then it writes down the equations. Or Spice, which is in the electronic world. Dimula is a company which is built on this. It has just been bought by Dassault a few years ago. So Dassault is really following this as well. And so you model uniphysics component, little pieces. One capacitor, one resistor, one piece of rod. You take everything, you put it together as a network. Then you identify what are the input and output parameters, what goes in. We've just done that here with a device, putting in the cable. And then you take that big model and do numerics and control. Oops. So if you look at the dynamical behavior of such a thing, that's a so-called differential algebraic equation. We saw yesterday the Euler-Lagrange equations. They are a differential algebraic equation. So it's a mixture between differential equations and algebraic equations which describe the interfaces or constraints. And that immediately brings in a geometric factor into the whole thing. So it's a dynamics constrained by algebraic equations or inequalities, and that means it's dynamics on some manifolds or some other geometric structures. And so the typical way how to write this nowadays is you have an implicit differential equation. Implicit because there are algebraic equations which do not use the derivatives. You have some initial conditions at some initial point, and you have typically also an output. That's what you can observe in the system. So t is time, x dot is a time derivative, and f describes some function on some domains. X denotes a state that could be finite or infinite dimensional if it comes from a partial differential equation, and finite typically if the partial differential equation has been discretized in space. U is an input or control, and Y denotes an output or measurements. So where do these applications come from? It started with electronic simulation, and the constraints are coming from Kirchhoff's laws. But the second most popular area is mechanical multibody system. So every car, airplane is like that. If you look at the flow simulation, we heard yesterday about it, if you have conservation laws, they lead to, after space discretization, to algebraic constraints, metabolic networks. So we ourselves, every cell of us can be described by a differential algebraic equation, and the mass balances describe algebraic equations, and so on. Essentially all areas of dynamical system, and we will get there in the future that pretty much for everything we have such a Lego box of models which you can put together. And it writes down equations, and then they give it to us as mathematicians, and we have to work on them. So just to give you the easiest example, suppose you have such a robot arm which has different joints, and suppose you want to use it to clean a window or to polish the surface of a car or something like that, or to weld. You have to model each of these rods. You have to model the end effector, which is a side part at the end, and you can write everything down using the Lagrangian equations of motions. So this is typically a nonlinear system, and since you have here at the end effector and also in the joints you have constraints, you have to add an algebraic equation. Psi of theta equal to 0. So theta is a vector of the displacements in the joints or at the end. U is a vector of control torques, and M is mass matrix, C is centrifugal and Coriolis forces, G describes the gravity, and you have a constraint strength function, which is typically a nonlinear function. And you usually put some sensor at the end of the robot and to figure out whether you are really there with enough pressure to polish the surface or something like that. Now, let's look at this. If this function is given, and that describes a position is described by a vector in 3D, then also the velocity that is applied at that point is given the same direction, and the acceleration as well. So that means within the equations hidden, and analytically we wouldn't care because it's automatically satisfied, there are extra constraints. Constraints for the velocity and constraints for the acceleration. These are the so-called hidden constraints. And which means implicitly there are algebraic equations for the derivatives hidden in the system. Now, as long as you do it completely analytically, it's fine. And that's what's happened between 1870, when the first DAEs appeared in Kirchhoff's laws, and the mid-70s, when everything started to become automatic. And then all of a sudden, one had to worry about these extra derivatives, because if you have a user numerical method, it has to also satisfy these constraints, and it doesn't. My favorite story is the flying trains in the German ICE system in the first modeling of Siemens, while the French TGVs never flew, even though they're faster, because it was done analytically. So this is the so-called drift-off phenomenon. And there are extra problems. The control problem may not be solvable. So let me give you one real-world example. This is Mercedes, and I had a project with Daimler, and to just give you a little view how terrible the modeling of such a thing is. This is an advertisement film from Mercedes. That's the current 7-gear transmission of the E-Class. And just to show you how many different parts are put together. And you have to model all this, and you have to write down equations for all of this if you want to do a model-based simulation and control of such a gearbox. And so in this project, you have to model every different part. That's a multi-body system, most of the part. Then you have to multiply the elasticity in the parts when they push onto each other. You have to model the friction between the parts. Actually, there's also a nasty oil film in there, which you have to model. And what the idea of Mercedes was that we create such a model, and in 2017, when this comes on the market, the board computer of your car is pretty powerful enough. And then you can maybe control the gearbox with a board computer. And why? This is much cheaper. Mathematics and computer science is extremely cheap compared to very accurate production. So then they could loosen the production of the parts. And the goal was to decrease the fuel consumption and improve the smoothness of the switching. I will show you some results of this at the end. But there is some dangers with this approach. And so this black box modeling with DAEs, it's extremely easy. So the modelers in the departments in industry, they have it easy. They just click, and then it writes down the equations. But the numerical simulation doesn't always work. There are instabilities and convergence problems. To get consistent initial values is very difficult, because the initial values have to lie on the manifold where the dynamics takes place, and it's hidden in the system. The solution depends on derivatives of the data. You have this drift off. If you want to run it on a board computer, you have to use a small model, a replacement model, and control is in general very difficult. So black box modeling is great, but it pushes all the difficulties into the mathematics. Now, for us, it's essentially, from a point of view of mathematics, it's work for centuries that will come there, because it gets more and more complicated equations that we have to deal with. Okay, I will give you a few slides of DAE theory if you're not familiar with that. So we do something which yesterday I heard in one of the talks you wanted to not do. You first of all do a so-called behavior approach. So you forget about the meaning of variables. So you call them variables, whether they are input states or outputs. It doesn't matter from a mathematical point of view. You call them that. But from the point of view of an engineer, it does matter. So that there is a first deviation from the way we treat this. So you introduce a new variable z, and then you put all the variables together and you have an implicit differential equation and some implicit initial condition. Since we know that derivatives may occur, you have to bring the derivatives into the game. And you do this by so-called derivative arrays. what are derivative areas. So you take your original equation and you differentiate it. And the mu, the little mu here, the index mu here, says how often do you do that. So you take your equation, you differentiate it with respect to time. Then you get, by the chain rule, you get higher order derivative, and you put everything together in one big array. That's a so-called derivative array. It's an idea of Steve Campbell. And then you solve this system. Now you made the problem harder, but at least all the information that you need, the hidden information, is in there. You don't know which one, and for practical purposes you don't want to differentiate everything, but if you don't know, you put everything together. And then you look at this as an algebraic equation. So you look at this as variables. Z dot is an independent variable. And then you can define such a solution set algebraically. And that solution set includes all the constraints that are in the system. The ones that were there originally and the hidden ones. And the dynamics lives in a subset of that set, which typically is a manifold. And then there's a terrible hypothesis here. This is just to make the nonlinear analysis work. I just wanted to point two things out. We assume that something is a manifold, and then some rank conditions. Rank conditions which describe which equations you need to pick. And these rank conditions may switch and things like that. I don't want to go into this detail, but you can show calling the smallest mu that you have to take to get all the information out. That's the so-called Strangeness Index. It's the number of times you have to differentiate. And then if the hypothesis holds, then you can pull out of the system two equations. One, which is completely algebraic, and that describes geometrically the surface on which the dynamics takes place, and another implicit differential equation which lives on that surface. And some redundancies. So as a mathematician you would say, why do I write this down? Well, in practice, when you model automatically, you always get redundant equations. You always get equations, extra equations. A is connected to B, B is connected to C is connected to A. They form a circle. If it's stiff, this is one equation too much. In practice, it doesn't come out 0 equals 0. It comes out 0 equals epsilon, and then you are in trouble because you have to get rid of that epsilon. That's I'm pushing all these difficulties under the carpet, but I'm mentioning it here. So this first equation, that should not be a curly here, this first equation describes the dynamics. And you see, the variables are still the same. There's no change of variables that took place, no other coordinate system. It's just equations. And what you have done in this way, you found a new model. And this model has a big advantage because it describes the manifold. It describes the constraint. And then you can do the geometric analysis on the system. So let me just explain this for this multi-body system. So this is the first order formulation of a multi-body system. So the first part is just the second order differential equation. This is a constraint. It has been put in by a Lagrange multiplier into the first equation. So we have the Lagrangian formulation of the equations of motion. And as I told you, the first and the second derivative of this constraint also needs to be added to the system. So in this case, we know what to differentiate, so we just add these two equations to the system. and we add 2 more Lagrange multipliers to bring these equations into the system, and then you are in that form that I had in this system. In general, there's a lot of work to be done in a general model. So for multi-body systems, it's well understood. Okay, so now, why did I do all this? Because I want to get rid of the difficulties in the numerical simulation. And when you have this formulation that I just showed you, this F1 and F2, you just throw away the 0 equals 0 equation, or make it 0 equals 0. That's a regularization that you do. And then what you do is you solve the problem, for example, with a backward difference method, so backward Euler method, for example. You just replace, you just take this algebraic equation which describes the manifold, and you solve it at every step. That means your algebraic variables are correct, and that means your x in particular is correct. So that means you have initial conditions. You know you are on the surface. And then you pull out the differential equation, that's the F1, but we don't pull it out exactly. We don't have to pull it out exactly. It's enough if it's pulled out with some accuracy. And then you replace the derivative by some finite difference, and then you run this, and this is what you do at every step. And then you can show that if the hypothesis holds, and then the Jacobians in the system, they have full row rank at the solution, provided the step size is sufficiently small and this approximate pulling out of the equations is sufficiently good, whatever that means, I didn't specify it here. Then you can use Gauss-Newton's type solvers at every step. And the order and the convergence properties are the same as for if you would have a standard ordinary differential equation or time integrator. And you can implement all this with local operations. That means you can do it step by step. Show you one movie. This is a ball on a parabolic surface that is driven by gravity and no friction. And if everything goes well, it should end up at the same point where it has a periodic movement. It should end up in the same. If you try this with any standard method, it will not end up at the same point. And so you can see the surface that it generates. And you can see this parabolic surface, and there it came back to the original point. And the thing is, this works because all the constraints are preserved. Now that sounds too good to be true, because you write down some general problem. What is a catch? You can do this. There's this hypothesis, which is admittedly rather tricky, but that you need to prove something nonlinear. But it works very nicely, this approach, in all areas, in control, in optimization, and we will see that. And at every step, but the cost is, at every step you have to do this derivative array, or you have to know what you have to differentiate. And the Jacobians have to be computed. Now, if you think about the Mercedes model that I showed you and look at all the parts, and possibly each of them are finite element models, it's a gigantic system. And So for this general approach doesn't work. And a lot of work that we're currently doing is to bring in physical information. And we're back at Lagrange. What we heard yesterday, that somehow the physical, you said that the physics has to be somehow reflected. You cannot just do it mathematically. I mean, you can, but then it's very, very expensive. But in principle, you can do that, and this is currently done with these modeling packages. But now, let's come to optimal control. So now we have equations which already use Lagrange multipliers to put the constraints in. And now you want to optimize. And you want to do what Gerd Wanner showed us yesterday. So how would a optimal control problem look like? You would have some function which weights the endpoint, and you would have some integral over some other function which describes the cost, the energy that control, and you want to minimize that, subject to a constraint which is such an implicit differential equation. Now you could do what we heard yesterday. You could just add the constraint into the system by Lagrange, extra Lagrange multiplier, and do variational calculus in that even more big space. That's essentially Lagrange squared. So already your equations have Lagrange multipliers, and now you use them to build up an even bigger system. I will explain all this on the linear case. It's a little bit easier to explain, and then one sees a little bit more. So in the linear case, the so-called linear quadratic control, you have a quadratic cost function and a quadratic weight endpoint weighting and the quadratic cost functions. And now a linear differential equation with a time-dependent coefficients. So that's the so-called linear quadratic problem. And the question is, can you find the optimal controls? You can do this all in a more general space, but okay. Let's go back to ODEs. We heard that yesterday. In the ODE case, you just add lambda times the constraint to the integral, and then you do calculus of variation, so you vary x, u, and lambda. And so for a minimum in the neighborhood, it has to go up. The solution has to grow, and then you get the Euler-Lagrange equations. They look like this. So here is the original equation. I leave off the dependency on t. That's the adjoint equation that we heard yesterday. That's an equation for lambda, differential equation for lambda. And I write it in a funny way. Gerhard Wanner pointed out yesterday that Lagrange and Pontryagin and others have different signs. And I write it in a funny way. You will see a little bit later why, because it's good for the geometry. And then you have this optimality condition. If the R matrix, which is the weight matrix on the input, if that is invertible, then you can solve for the last equation, for u, and get rid of the u. So if R is invertible, you can turn this into such a boundary value problem. You can write this as j times lambda dot x dot equals a. A is symmetric and j is this skew-symmetric form, and A is this matrix. And then you can take the inverse of j and put it over to the other side, and you are at Hamiltonian. There shouldn't be any dots here. Should be just the variables. That's a copy and paste mistake, I just noticed. So H is A times J, and that's a Hamiltonian matrix. So that's the Hamiltonian system. In the linear case, it's easy to describe. And this differential equation has a symplectic flow, which means that the fundamental solution matrix is orthogonal in the inner product defined by the J. Okay, so then you just have to solve this boundary value problem. It's a nasty boundary value problem because half of the initial conditions are on the left and half of them are on the right. But nonetheless, that's the boundary value problem, and it looks very similar in the nonlinear case. Now, how do you solve boundary value problems? In the 60s, very famous mathematician Rudi Kalman from Hungary, later on at ETH, he showed that if some extra conditions hold, then the optimal solution is a feedback. The optimal solution can be written in the form of a matrix times the state. And X, this capital X, is a positive semi-definite solution of a Riccati equation. So a quadratic equation. So if you take time to be infinity, and so you go over an infinite interval and constant coefficients, it's an algebraic Riccati equation, and otherwise it's a Riccati differential equation. Now that's great because it takes a boundary value problem and turns it into an initial value problem. So this is an initial value problem. It runs backwards in time, but who cares? It's an initial value problem. It's great. Unfortunately, the dimension is squared. And if our dimensions are already big, then this may be a problem. But nonetheless, this is a fantastic idea that you have a feedback. And that's actually what makes control really feasible. All the controls that we see in life, in real life, even in ourselves, are feedback controls. If I walk over here and I step over this thing at the bottom here, then I have a controller in my body which has learned how to react on certain movement. It's a feedback controller. I react on the current state. And furthermore, in the work of Kalman, there's also shown that if the Riccati solution is X and is positive semi-definite, but symmetry is enough, then there's a space, identity X, which is a Lagrangian invariant subspace of the matrix, corresponding to the eigenvalues in the left half plane or the right half plane in the constant coefficient. And you could sometimes even the converse hold. And so such a subspace is called Lagrangian if it's n-dimensional in the 2n-dimensional space and it's neutral. That means U transpose Ju is equal to 0. So Lagrange is there again in the representation of the space. And you can actually take this space and put an identity here and a 0 here, and that's the matrix which decouples the forward and the backward integration in your boundary value problem. There are some difficulties with this approach. First of all, it works only for the linear case. Second of all, the R matrix, the cost-weight matrix, may not be invertible, for example, in differential games or robust control. Or the inversion may be bad from a numerical point of view. In the PDE control case, the Hamilton function may be a full matrix that cannot be stored even if the data are sparse, have lots of zeros. If you use a boundary value problem approach and just discretize, then it's very important to preserve the simplicity of the flow. And it's not so easy to do this. There's a famous book by Haira, Lubich, and Vanna on geometric integration, which does that. There's a lot of work on this. But it's not an easy task. But essentially for the ODE case, everything's pretty much settled. It's put into software there, and people can use it. There's a library that is used by in industry, by Airbus, that we wrote, that does this. Now you go to this DAE case, this general implicit case. Is there anything to do? We heard yesterday about Pontryagin approach. Why don't we do that? Why don't we just write down the Euler-Lagrange equations? Differentiate, add the thing with the Lagrange multiplier to the system, differentiate everything. Now there is a little problem because DAEs are not always solvable. And if you want to use that, you need a solvability result. So for linear ODEs, for example, we always have a unique solution, but the DAEs where this E may be singular, or in the general nonlinear case, there may not be a unique solution, and then this approach doesn't work. It doesn't necessarily give you the minimum. And one also has to do a little bit more on the spaces. But you could do a naive idea. I mean, that's what you find in the engineering literature. You just put an E where the identity was and hope that it works. So that's, let's call this a formal optimality system. So that's the original equation. That would be the adjoint equation if everything would work and all the differentiation and everything would be solvable. So it looks exactly the same except that I put an E here, here, and here to make it correct from the using the product rule. But in general, this is not the correct system. Here's an example. Very simple one. So the cost function is 1/2 x1 squared plus u squared. And this is a differential algebraic equation. You can do the calculation by hand. It's analytically, you get that the x, the u, and the lambda are of this form. And here you again see that derivatives of inhomogeneities appear. And x2 is minus f2, and lambda 2 is equal to 0. So that would be the optimal solution. If you write down this formal optimality system, everything looks the same, but the lambda 2 is not 0 anymore, but it's 1/2 f1 dot plus f2 double dot. And all of a sudden, another derivative appears which was not there before, a second derivative. So you need more regularity, and also this initial condition is not used, which is true in the original system, in the correct solution. So there are many more examples like this. This is the simplest one, where we can show that things go wrong. If you want to really get the optimal solution in the linear case, what you have to do is you have to introduce other spaces. So in the classical solution setting, what you do is you use a projector. E plus is the Moore-Penrose inverse of a matrix. That's the generalized inverse which satisfies these equations. And E plus E is a projector on the kernel. And E plus is a projector on the co-image. And you use this space, and in this space, this is how the optimality system looks like. It's pretty ugly. But you can see what happens here is there's projectors here that you have to pull in. These are the projectors on the manifolds, so to say. These are linear manifolds in this case, but these are projectors, and you have to make sure that your dynamics sits on the manifold, and you have to make sure that the adjoint equation also does the right thing. And so you get a much more complicated system. But in principle, you can write it down. And in principle, you can also compute these projectors, but not for a large-scale problem. There's one difficulty. Since we have all these projectors in there, it's not this matrix R which plays a role, but that the invertibility has to be in some submanifold, and that may not be the case. So then this is again a DAE. We heard that already yesterday, and this DAE may not be, the manifolds may not be identified there. One has to do this again. It's very complicated because by the cost function you can change this behavior of the system, and in some cases you can even get a feedback control. And there's a similar result for the nonlinear case. But here is a completely surprising result. Suppose you take this formal system that I wrote down here, and suppose that it has a unique solution. Then there exists another function, eta, which is a virtual Lagrange multiplier. It's not the Lagrange multiplier that you put in order to do the optimization, that replaces the lambda such that x, u, and eta solves a true optimality system. So in other words, the x comes out right, the u comes out right, but the Lagrange multiplier comes out wrong. Now the question is, do you need it or do you not care? Now this is very interesting from the point of view of applications. In most cases, a Lagrange multiplier is just an artificial variable that you add in order to solve the optimization problem. Later on, you throw it away. But in the Lagrange equations of motion, the Lagrange multiplier actually is a force. It has a physical meaning. It's the force. So if you have two joints, so in such a robot arm, like here in my arm, it describes the force which takes this thing apart. So then the Lagrange multiplier has a physical meaning. It would be good to get it correctly, because then you would know whether my arm is torn from the upper half of my arm. So whether you can just ignore it or not, that depends on the application. But in the optimization situation, usually you don't care about the Lagrange multiplier, and then you can just ignore it. Now, if I write down the optimality system, and I write down the coefficients, they have this form. In the constant coefficient case, they form a matrix pencil with a skew-symmetric matrix and a symmetric matrix. So if you look at that that function in lambda, that's an even pencil. It's because L of lambda is L transpose of minus lambda. That reflects in the eigenvalues that are there. They are symmetric with respect to the imaginary axis. But more, it's a skew-symmetric, symmetric problem. I wrote it down in a specific way, the equations, so that you see this. This here in the corner sits the J, which describes the symplectic flow, and then the other part is symmetric. So if we would solve the boundary value problem directly, as I mentioned, you could use finite differences or finite elements or collocation methods, and then you have to solve a huge linear system which has a size 2n by capital N, where capital N is the number of discretization steps. For good convergence, you may need a lot of discretization steps, and this should be block tridiagonal here. There's a tri missing here. It's medium sparse. There's k2n blocks per row, but due to the boundary conditions, it's not a banded system. So it's not so easy to set. Sparsity of the blocks would help. and you get the optimal u and x, but usually not in a feedback form. Feedback would be ideal. And there may be a storage problem when you really solve this with a PDE, because if n, the dimension is already large, and now you do lots of steps, then this is a problem. And there is another problem. If you do this way, and you don't use a geometric integrator, the simplicity of the flow that you know about is gone. You can write down Riccati equations for this as well. They look more ugly. Essentially, there are lots of more e's in there. If E would be invertible, then you would still get a feedback. So you would get that the solution is a feedback matrix where X is derived from this Riccati equation. And yet then you can, here, that's the feedback matrix. And then you can solve it in the same way. If E is singular, you can use the pencil approach. But the size, as I mentioned, is n squared. And n squared may be too big if n is already big. The matrix X has to be stored because the solution is later on, the X solution is gotten from this differential equation. And this X matrix is a matrix that is time varying, and that has to be stored. If you cannot store it, then you're in trouble. There are lots of ideas with low rank approximation. There's a lot of work currently going on to get this cheaply. There's a third approach, which uses, in the constant coefficient, which uses eigenvalues and invariant subspaces. And we have seen already this Lagrange subspace. And there's an extension of the Lagrange subspace. So you take that matrix pencil, and you find a subspace with 3 blocks. So n by n, n by n, m by n, where m is the number of inputs. And then if everything works out nicely, and this is really true, n by n, then the Riccati solution is this. So you multiply from the right by here, use a different representation of the subspace I, X, and then it's a Lagrange subspace plus some extra garbage in the bottom. And actually, this garbage in the bottom gives you the feedback. And this can be generalized to the time-varying case and onto the nonlinear case. So we say that a pair of matrix functions, so previously we had skew symmetric, symmetric. For matrix function, you need skew symmetric and this condition due to the product rule. And you can show, using the right spaces and the right function analysis, that the operator, the differential algebraic operator, is self-conjugate with respect to some appropriate bilinear form. And that means you can do this approach with the spaces, extended Lagrange subspace, in a similar way as in the constant coefficient case. And actually, that means, again, the optimality system follows from a variational approach in a admittedly complicated space. But you can write it down as a variational formulation. And so, again, Lagrange comes into the game. And you can even show in the fully nonlinear, under some constant rank conditions, that you have a Hamiltonian subsystem and the flow is symplectic on the manifold. So now you have a manifold and a flow on the manifold, and the flow on the manifold is symplectic. And again, we have an extended Lagrange subspace. So at the end, let me go back to the transmission. So I showed you this movie. That's a current transmission. This is how the transmission in 2000, if you buy yourself an E-class, will look like. It's slightly different. It's such a variator. It's a continuous transmission. No more switching from one gear to the next. It switches continuously. And it switches by pushing these two geometric parts together, and then these parts are pushed out or in. That already was in the 60s a type of transmission in a DAF, and Volvo has that. And now it's becoming very popular. So you have this hydraulically, you have these two parts here, and they push together, and then there is this part that's pushed up and down. So you have to model all this. This is a verification between experiment and simulation. Now, from a mathematical point of view, that doesn't look very accurate, but from an engineering point of view, that's just perfect. This is a controller that we built. So the red curve was supposed to be done, and then the blue curve is what we did. The thing was a complete failure. Why? Well, every single part, the simulation worked quite well. But when we built the controller based on the model and compared it to the controller based on the prototype they built, they were not the same. And they are very conservative. This is German car industry, very conservative. They don't put anything in which they haven't tested in lots of experiments. So my student who worked on this together with 9 other PhD students, they learned very quickly that model-based at the moment is not good enough. Not compared with some hardware engineers who build such a thing. On the other hand, to build a prototype costs 10 million. And every time you change it, you have to invest again. They would like to do it model-based, but it's our task to make this better. And it's not only in cars, it's everywhere. So let me conclude with DAE constraint systems, optimal control problems. They are Lagrange squared, in the sense that they use Lagrange multipliers to couple in a system which has already Lagrange multipliers. They have a nice structure. There is a variational principle behind. And it comes back to Lagrange in the old times. And the reason is now, at that time he wanted to make things simple because he wanted to do it by hand, and nowadays we want to make things simple because we want to do it on the computer. Just the model size has grown a little bit. And there's a very nice geometry behind the thing. I didn't have time to talk about this, but there's a really nice geometrical interpretation about the whole thing. And in a certain sense, you could say Lagrange is life and kicking. And with this, I would like to